Welcome to Rahandran. So, in my previous video on electrostatics, I discussed about the electric field, the electromagnetic force field. So, I discussed the uh, basic introduction of a force field in engineering terms. Okay, so it was not that technical in terms of physics, I guess, but in terms of I wanted to uh, convey that electromagnetic fields are physical phenomenon, and it's a physics thing. Okay, and what we who study engineering uh, do is we try to explain this physical phenomenon, this physics things, in terms of application. So in terms of applied physics, how do we explain electromagnetic fields? So I was trying to explain that from engineering lens. So I hope you understood my previous videos, not just the immediate previous video, the other previous videos too on electrostatics. So in particular, in my previous video, I discussed about the force field, electric field strength, and electric flux and flux density. So now today I'm gonna talk about what is the cause of this electric flux from classical applied physics point of view, not quantum electrodynamics, quantum field theory, because I myself don't understand about those things. So it is also very hard to grasp those things, because obviously uh, only a very handful of people in the world can really understand this kind of dynamics and interrelation, cross domain relation of the force fields. So so back to my explanation, back to this video. So today I'm gonna try to explain the source of electric flux. Okay, so flux, the electric flux, which obviously exists in 3D space, okay, near the source or sink. So phi d electric flux is the scalar quantity which determines the total electric field effect throughout 3D space, and electric flux density, or this d, the flux, total flux per area, is the calculation of electric field. It is direct calculation. So flux d, flux density or flux per area, total flux per area, d, is the calculation of electric field intensity, which is especially describing the field material interaction. So flux density especially describes the field and material interaction, because in my previous video I discussed about a little bit about permittivity, electric permittivity. D as a vector is related to the electric field intensity by epsilon, which is the permittivity. So epsilon is also epsilon o, epsilon r. Epsilon r is called relative permittivity or dielectric strength of a material. So this is what it is. So now our question arises from our mind, that what's the source of this electric field, or is the electric field source itself? So from my previous video, if I have talked about or I may not have, so fields are more fundamental to uh, a physical world, and in the study of quantum field theory, uh, that it states that field is independent of particles. it can, they are related, but fields can exist without particles. And quantum field theory states that um, electric electrodynamic field or any other fields are fabrics of the reality. So it's very fundamental and very deep, so I don't understand myself what that even means, to be the fabric of reality. So from my engineering mindset and practical uh, applied physics perspective, the source of electric field, hence flux density, hence flux, what is the source? The source of electric field is the charge q. So you have to distinguish that the charge is not particle itself. Charge is the property, it's the fundamental property of particles. So the particles which have charge are also a source of fields. Okay, or we can say that particles with charge can interact with electromagnetic fields and other fields. Um, Especially when we talk about electromagnetic fields, we talk about uh, charge, and there's also spin. So charge and spin are two fundamental properties which determines how a particle interacts with electromagnetic field especially. And if we want to uh, directly relate field and particle, especially electric field and charge, so the direct relationship is that the electric flux is literally equal to the charge enclosed by a surface. Charge is literally equal in quantity, in value, with the equal to the uh, electric flux. So there's a corresponding law in electromagnetics called Gauss's law. I'm going to talk about that now. So this also tells us that, so it is very important realization, this relationship, that electric flux is literally equal to charge enclosed by surface. Okay, so this is very important, enclosed charge. And this also tells that the divergence and convergence also, when we say that electric flux is equal to enclosed charge, charge is the property, okay, not the particle itself. So when we say that in electric flux is equal to charge, we say that we can replace the existing electric charge with the electric flux, the divergent or convergent electric flux, eh, at a point, idea of charge existing at a point, say this is the point, and this charge can be replaced by electric flux. So q is literally equal to phi d to a closed surface. So in 3D space, the closed surface is a sphere. Those who don't know, that closed surface is a sphere, obviously. So and this is very important realization, that charge itself is the flux or source of flux, or flux is the source of charge. It can also be said, it can also be vice versa. So phi d isn't a side effect of q. Q isn't a side effect of phi d, phi d isn't a side effect of q, but q is quantized, charge is quantized, and phi d is continuous and distributed. So q, charge, the property, this is also a fundamental law. I think it is the Planck's law, I guess. So charge is quantized and discrete, whereas phi d is distributed and continuous. Distributed and continuous. So this is very important, and we can also say that q, the charge, isn't separate from the electric field, rather charge is from which electric field diverges or converges. Charge isn't separate, it is what to say, it is entangled, or it is one in the same in some cases. In some cases they can be separate, so there's a lot going on here. So charge is the field's divergence. So this is also a very important thing, the charge is field divergence. Q, charge q is field, so electric field, so electric field divergence. This is also a very important realization, which is directly the Gauss's law. So this also indicates that conduction isn't the only mechanism for transfer of energy and momentum. Okay, so that's also because without charge field exists, and field is what stores charge and momentum. So it's very important, and I hope you understand this. Now I'm going to talk about Gauss's law. The realization I found, and I hope you understood that realization, that the source or sink of field or electric flux, to be exact, which is the quantity of the field, the vector field E. So the source or sink of it is directly related to charge, which is the property of particles and materials. So electric charge is directly equal in value with the electric flux, and charge is discretized, quantized, but flux is the version, the distributed continuous version of the charge, and vice versa. Charge is the divergence of electric field itself. So very entangled, and in so deep, such a deep interrelationship that it's kind of uh, I, at this stage impossible for me to differentiate explicitly which is which. Okay, so I hope you can somewhat understand. If you have some other ideas to differentiate charge and the flux or field in a more fundamental way, which is applicable in real world, you can tell me on the in the comment sections. So now I'm gonna state and discuss the Gauss's law. So what Gauss's law states is that it's literally the same thing that I just said, that charge is the flux, charge is the field divergence. So total electric flux through an enclosed surface in 3D space, the closed surface is always a sphere. So which is the any closed surface is equal to the total charge enclosed by that surface in 3D space, which is a sphere basically. So divergence and convergence of a field is the charge itself enclosed by that surface. So divergence of a field of electric field in 3D space is literally equal in value. Divergence of electric field in 3D space is literally equal in value to the enclosed charge in that 3D space. So this is the full relationship. So enclosed charge is the uh, closed integral, surface integral of the total flux, which can be uh, denoted by the flux density. Flux density is the flux per area. Total flux per area is flux density. Then um, this is the divergence theorem. So closed surface is volume by definition in geometry. So it can be written like this: the divergence of the electric flux density over a volume, and which is literally the divergence of flux density is literally charge density, which is volume charge density over that volume, which is equal to the total flux. So this relation, this particular part of the Gauss's law, gives Maxwell's first law, and which is law for electrostatics, that divergence of flux density, this is divergence. So this is nabla or del operator, this is vector differential operator also. So divergence of d is the volume charge density in 3D space, which can be also stated like this: divergence of electric field intensity is volume charge density by epsilon. So this is also Maxwell's first law, Maxwell's first equation or law. Or so now that I have talked about Gauss's law, so if you say that this point from which charge is condensed and is diverging, so this divergence along this closed surface, say this is d phi d, okay, and in this closed surface say a, so da da. So in this closed surface the flux is equal to the enclosed charge, and over full 3D region it's total charge, obviously it's total charge, which is by value is the flux itself. Okay, my last thing will be uh, talking about what are the other sources of electric field or electric flux. Okay, so electrostatics deals with stationary charges, the charge carriers, the or charge accumulation that is stationary in 3D space, which is not moving, okay, relatively or literally. So charge transfer, meaning that movement of charge, or transfer meaning I am giving charge to a body or taking charge from that body. So charge transfer is the fundamental process behind electrostatic field generation. So when I say that how is the static field generated, it's probably generated by charge transfer. Okay, remind you, charge is the fundamental property. It doesn't necessarily mean electrons. Okay, any body that has charge, which is the fundamental property, can uh, produce electric field. Okay, can be a source or sink of electric field. Electrons are sinks of electric field when electrons, because electrons carry charge. Okay, so also when electrons are stationary, it acts as sinks of electric field or flux. So charge transfer itself involves current density and epsilon, which is the material um material interaction, the how we quantify that material interaction, and that is the permittivity of material. Now uh, I'm gonna list some processes uh, by which we generate electrostatic field, even electrodynamic fields also, but my main focus will be electrostatic field. So there are mainly uh, two uh, there are mainly two mechanisms. One is induction, and other is direct contact. Direct contact or conduction. So these are the two uh, main I mean these are the only two methods by which we can produce electric fields, electrostatic field mainly, and electrodynamic field also. So any kind of fields we can generate by induction or or indirect contact. This is induction is also called a distant influence. Okay, influence from a distance. Indirect contact and direct contact, which is conduction. So these are very important. So conduction can happen, conduction can be two types: sustained conduction and transient conduction. Sustained or steady state conduction, which is called current, and transient conduction. Okay, so these are the two methods by which we generate electrostatic field. Even electrodynamic field is also generated by induction and direct contact or conduction. Okay, so I'm going to talk about that uh, these two briefly, not that in details. So there are several physical mechanisms that acts as effective induced or apparent sources of electric flux even without free charge q, even without free charge, like q charge q, not q, say free charge is electron obviously, or ions. So several physical mechanisms, so among which induction and conduction is directly due to free charges. Okay, conduction cannot happen without free electron charge carriers, and but induction is very important. Induction is the real mechanism behind inductor and capacitor, mind you. So there's there are many types of inductions: electrostatic induction, which I'm going to talk about in this video. There are electrodynamic induction, electromagnetic induction, and magnetic induction, purely magnetic induction. So induction is very diverse and it's very interesting. So uh, so by induction we just, what do we do is we take a body with say negative charge, a net positive charge, and if we bring it to close to a neutral body. So if we take it close to a neutral body, it will induce net negative, uh, sorry, not net negative, it will induce negative charge near its surface where the positive charge is closest. So it will induce a negative charge near the surface, and under the surface it will be positive. Now what, this is a temporary charging uh, of electric field generation, for electric field generation. So now if I take this and ground it, the net negative charge, sorry, the extra charge will go to this positive side, and then if I take this net positive charged body out, then it will remain and at the same time I remove this grounding, it will remain a net negatively charged body, hence it will produce electrostatic field. So this is the generation process of electrostatic field via induction. And there's also induction is done by polarization. So which is the process of induction is polarization in materials. So this is not directly polarization, but uh, polarization is a part. So when the body is polarized, it's not charge net by it doesn't have a net charge, but it's polarized. Okay, when the body is charged, it's permanent, it does have net charge. Okay, it's not neutral anymore. So polarization is the induction is done by polarization. So the limiting factor of polarization is the ionization. The process ionization is the process of producing free charge carriers like electrons ion. The process of producing charge carrier is called ionization, and polarization is just the separation of positive and negative charge, but the body remains net neutral. Okay, so this is induction in brief. Then direct contact or conduction. So here in induction I didn't directly touch the two bodies, but what happens if I touch the body? So now I am touching the body. So what will happen is the electrons will go to this body and try to neutralize it, but this won't be neutralized. So what will happen is relative to this body, this this initially positive body will become neutral, and vice versa relative to this positively charged body. Due to direct contact or conduction, this will become neutral at first, because this body A was positively charged and this body B was negatively charged and wasn't directly touching or in contact, directly contacting each other. And with respect to each other, body B would be negatively charged, net negative, and body A would be net positive. But when we touch the two, extra electrons will go to this, and relative to each other they would become neutral. But if after touching, when they have transferred enough charge, if we um, take them apart, they one will become net positively charged and the other would become net negatively charged. So this body A would become net negatively charged. So this body would be net negative, body A, and this body would be net positively charged. So this is the electrostatic field generation via conduction. Sorry, this is divergent, and this is the electrostatic field generation via induction. So that's it for today. I hope you understood my explanation. If you have any problem, do tell me in the comment section. And I thank you for watching the video thus far. And I am trying to make videos as much as possible in my spare time and as detailed as possible, and you can see that my most of my videos are very large. It's because I am trying to discuss about this in details, because I think I don't find this kind of topics discussed in details in other videos on YouTube, on the internet. So I hope uh, you have found this video and my other previous videos, if you have watched them, useful for you. Thank you so much.